It begins with the raw darkness of space. Silent, endless, and cold. You're floating there, weightless, staring into an infinite ocean of stars. Then, without warning, one of them begins to change. At first, it's just a faint flicker, barely noticeable among billions. But this flicker is no ordinary twinkle. It's a death signal. A signal that something massive, ancient, and uncontrollable has awakened. And if you're watching this from Earth, it's already too late. Most people imagine doomsday as an asteroid slamming into our planet, a nuclear war, or maybe the slow boiling of our oceans from climate change. But there's something far more powerful, far more unstoppable lurking in the universe, and it doesn't care about your borders, your weapons, or your plans. It's called a gamma-ray burst, and if it hits Earth, it will kill almost everything, instantly. But here's the worst part. It can happen without warning. No alarms, no time to hide. One moment, the skies are calm. The next, an invisible wave of energy tears through the atmosphere at the speed of light, shredding life like paper in a storm. Right now, somewhere in the depths of space, there could be a star, a ticking bomb counting down to its final breath. It may have been stable for millions of years, shining quietly, feeding planets with warmth. But massive stars don't die quietly. They explode, unleashing the most violent events the universe can produce. And in certain cases, they send out twin jets of pure radiation, focused and deadly, stretching across unimaginable
But WR-104 isn't alone. There are other ticking bombs scattered across the galaxy, each with its own countdown clock. Some are thousands of light years away, others much closer. The terrifying thing is, we don't even know where all of them are. The universe is vast, and most of it remains hidden from our view. That means the star that could wipe us out might not even have a name yet. To understand why these cosmic monsters are so dangerous, you need to know what actually happens in the final moments of a massive star's life. Imagine a core so hot and dense that atoms themselves are crushed. The star has spent millions of years fusing hydrogen into helium, then into heavier elements, building layer upon layer like the shells of an onion. But eventually, it hits iron, and that's the end. Iron doesn't release energy when fused, it consumes it. The star's furnace sputters, the outward pressure holding its mass together collapses, and gravity wins. In less than a second, the core implodes. This implosion sends shock waves racing outward, tearing the star apart in a supernova. But if the star is spinning fast enough, and if its magnetic fields are strong enough, those shock waves channel the energy into narrow, focused beams. These beams, gamma-ray bursts, contain more energy in a few seconds than our sun will release in its entire lifetime. And if one is aimed at you, well, you wouldn't have long to think about it. It's happened before. 440 million years ago, long before dinosaurs, the Earth was teeming with strange marine life, trilobites, coral reefs, and early fish. Then, suddenly, 85% of species vanished. Scientists believe a gamma-ray burst may have been the trigger, stripping away the ozone layer and letting lethal solar radiation fry the planet. The oceans turned toxic, ecosystems collapsed, and the world went silent. If it happened once, it can happen again. And here's the cruel truth: there's no defense. You can stop an asteroid, you can survive a volcano, you can adapt to climate change, But you can't stop a beam of pure energy traveling at the speed of light. The only real hope is to not be in its way when it fires. And yet, our galaxy is littered with potential killers. Some, like Eta Carinae, are visible to amateur astronomers, glowing brightly in the southern sky. Others are hidden behind veils of dust and gas, detectable only by the most powerful telescopes.
This is not speculation pulled from thin air. It's based on models published in peer-reviewed journals such as Astrophysical Journal Letters and monthly notices of the Royal Astronomical Society. These models simulate atmospheric chemistry and UV exposure following a nearby gamma-ray burst, and the results are consistent. The damage would last for years, possibly decades. WR104, the Wolf-Rayet A star mentioned earlier, has become a focus of concern because of its apparent orientation toward Earth. At approximately 7,500 light-years away, it sits just outside the most dangerous range, but the margin is slim. A margin that thin becomes even more worrying when you consider uncertainties in distance measurement and beam spread. Astronomers have stated repeatedly that while WR104 is not an immediate threat, the possibility cannot be dismissed entirely. The exact moment of its collapse is unpredictable. It could be in the next million years, or it could have already happened, with the burst currently racing toward us unseen. The concept of no warning is also grounded in hard physics. Light travels at about 299,792 kilometers per second. If a gamma-ray burst were to occur 5,000 light-years away, the radiation would reach us 5,000 years after the explosion. The moment we detect it is the same moment it arrives. There is no gap between discovery and impact, because light and gamma rays travel at the same speed. Some might ask, can our technology protect us? The answer is no, not in the conventional sense. Spacecraft shielding, underground bunkers, or even magnetic field generators cannot block gamma rays at this scale. The energy levels involved are far beyond anything human engineering can withstand over a planetary surface. The only realistic safeguard is probability, the hope that we simply are not in the crosshairs when one of these bursts occurs. Gamma-ray bursts have shaped the history of life on Earth. Studies have linked the late Ordovician mass extinction, around 440 million years ago, to a
To truly grasp the threat, we need to understand the mechanics of the gamma-ray burst itself. In the case of long-duration GRBs, the ones produced by collapsing massive stars, the process begins when the star's core runs out of nuclear fuel. Without the outward pressure from fusion reactions, gravity forces the core to collapse inward. This collapse happens in less than a second, creating either a neutron star or, in many cases, a black hole. As matter falls into this newly formed compact object, some of it is funneled along the star's rotational poles. The result is a pair of extremely focused jets moving at nearly the speed of light. These jets are what we detect as gamma-ray bursts. They are composed of high-energy photons, along with charged particles moving through intense magnetic fields. The energy density within the jet is extraordinary. In laboratory terms, we cannot replicate even a fraction of it. The beam is so narrow that its width over vast distances can be likened to shining a laser pointer from the moon and hitting a coin on Earth. The danger to Earth comes from being in the direct line of such a jet. Even at thousands of light-years away, the radiation could strip away much of the ozone layer. The effect is not simply an instantaneous blast. The chemical changes in the upper atmosphere would persist for years. With ozone depletion, ultraviolet B and ultraviolet C radiation from the sun would increase dramatically at the surface. For humans, this means severe skin burns within minutes, increased cancer rates, and widespread damage to the eyes. For ecosystems, it means mass death of phytoplankton in the oceans, the foundation of the marine food chain, and catastrophic effects on land plants. Short-duration GRBs, while briefer, are also lethal. They are thought to originate from neutron star mergers, which have been observed through both gamma-ray detectors and gravitational wave observatories like LIGO and Virgo. The August 2017 event, known as GW 170817, confirmed this theory when gravitational waves and a short GRB were detected from the same cosmic collision. While short bursts release slightly less energy than long bursts, the gamma radiation and after effects on the atmosphere would still be devastating if the event were nearby. Measurements of past bursts in other galaxies have shown energy releases on the order of 10 to the 44 joules, more than our Sun emits in its 10 billion year lifetime. The scale is incomparable.
From the comfort of a clear night under the stars, the Milky Way can seem eternal, serene, and almost protective. To the naked eye, it's a glittering band of light, a backdrop for quiet moments and ancient stories. But this gentle starry river hides predators, cosmic events so violent that, if aimed at us, could wipe out much of life on Earth before the mind has time to register what's happening. One of these predators is the gamma-ray burst, or GRB, the most powerful explosion known to science since the Big Bang itself. A GRB is the astrophysical equivalent of a sniper shot, except the bullet is a collimated beam of pure energy, traveling at the speed of light, carrying more power in a few seconds than our Sun will produce in its entire 10 billion year lifetime. And unlike the things we normally fear, earthquakes, hurricanes, volcanoes, a GRB offers no warning, no tremor, no cloud, no strange animal behavior. If Earth ever finds itself in its sights, we would know only in the moment it strikes. The deadliness of a GRB lies in its geometry. They are not spherical explosions, radiating energy in every direction like a light bulb. Instead, their energy is concentrated into narrow twin beams that erupt from the poles of the dying star or merging neutron stars. Picture the universe as a dark, three-dimensional battlefield. Each GRB is a laser pointer cutting through that darkness, harmless to all except the unlucky worlds caught in its crosshairs. That focus is a double-edged sword. On one hand, it means most of the universe is spared when a GRB occurs. On the other, if you happen to be in that narrow cone, a region that might span just a few degrees across, distance becomes the only shield you have left. The closer you are, the more devastating the effect. Astrophysicists calculate that a long-duration GRB, the type produced by collapsing massive stars, could cause extinction-level damage to Earth's biosphere from as far away as 6,000 light-years. At that range, the initial gamma flash alone could destroy a large fraction of our ozone layer. Closer than that, and the damage compounds dramatically, threatening the survival of complex life. Among the thousands of massive stars catalogued in our galaxy, one has drawn a disproportionate share of attention. WR-104, a Wolf-Rayet star in the constellation Sagittarius, roughly 8,000 light-years from Earth. Wolf-Rayet stars are rare, massive, and volatile. They are in the final, unstable phase of their lives, shedding their outer layers through powerful stellar winds. This rapid mass loss is a sign that their cores are burning through the last stages of nuclear fuel. And when that fuel runs out, their death is spectacular and potentially lethal to anything in the path of their gamma-ray jets. What's unsettling about WR-104 is the suspicion, based on years of spectroscopy and imaging, that its rotational axis, the likely direction its GRB jet would point, may be roughly aimed toward Earth. Astronomers analyze its light for subtle Doppler shifts that reveal how it spins and tilts. But these measurements are devilishly hard to get right. Even an error of a few degrees could mean the difference between direct exposure and complete safety. Right now, the data leaves us in limbo. We can't say with certainty that WR104's future GRB, if it produces one, would hit Earth. But we also can't dismiss the possibility. It's like knowing there's a rifle somewhere in the dark, possibly pointed your way, and having no way to tell if the trigger will ever be pulled. The silver lining, if it can be called that, is that GRBs within the Milky Way are rare. The best estimates suggest our galaxy might see a long-duration GRB once every few 100,000 years. For any given human lifetime, the odds are extremely low. But over the span of Earth's 3.5 billion years of life, once every few 100,000 years is not rare at all. It means multiple hits are possible, perhaps even likely. Some paleontologists and astrophysicists now suspect that past mass extinctions may have been triggered by GRBs. The fossil record contains abrupt collapses of biodiversity on land and in the oceans that do not correspond with asteroid impacts or volcanic super-eruptions, but show patterns consistent with sudden, intense bursts of radiation from space. If a GRB were to strike Earth from within the danger range, the devastation would begin in the upper atmosphere. The incoming gamma photons would slam into nitrogen and oxygen molecules, breaking them apart and forming nitrogen oxides, highly reactive chemicals that are ozone's worst enemy. The result would be a severe depletion of the ozone layer over weeks to months. With the ozone gone, ultraviolet radiation from the sun would flood the surface unfiltered. In practical terms, this means mass die-offs of plankton, the base of the marine food chain, within days in sunlit waters. On land, crops would fail under the onslaught. Understanding whether or not we are in that crosshair is where the real challenge begins. Astronomers rely on a combination of tools: spectroscopy to determine a star's rotation, high-resolution imaging to measure its orientation, and long-term observation to track changes over time. For potential GRB progenitors like WR104, this work can take years. WR104 is a binary system about 7,500 light-years away, home to a Wolf-Rayet star, one of the most massive, hottest, and shortest-lived types of stars in the galaxy. These stars burn their fuel so violently that their lifespans are measured in just a few million years. When they reach the end, they don't fade quietly. They collapse, unleashing an explosion so powerful it can punch through half the galaxy. The concern with WR104 is that some measurements suggest its rotational axis could be pointed almost directly toward Earth. That doesn't guarantee a gamma-ray burst will hit us, but it makes the scenario worth taking seriously. Even a small margin of error in our measurements could mean the difference between harmlessly missing the beam and being in the direct line of fire. And given the distances involved, any correction in our estimates could arrive too late. While WR104 has captured public attention, it's far from the only star that could produce a GRB in our galaxy. The Milky Way contains numerous massive stars in advanced stages of evolution. Most of them are scattered across quiet regions where the risk to Earth is negligible. But our solar system's 230 million year orbit around the galactic center means we periodically drift closer to active star-forming regions, the cosmic neighborhoods where GRB-capable stars are born. What makes gamma-ray bursts even more unnerving is that they operate on timescales far beyond human intuition. The odds of one happening in any single human lifetime are small, but across the 3.5 billion years life has existed on Earth, the statistical probability of multiple bursts affecting the planet is significant. Geological evidence hints this may have happened before. Some extinction events in the fossil record, where species disappeared suddenly across both land and sea, lack any signs of asteroid impact or prolonged volcanism. In these cases, scientists have found chemical traces in rock layers that match what we'd expect from a massive influx of high-energy radiation. Isotopes, like beryllium-10, formed when cosmic rays slam into our atmosphere, and unusual nitrogen oxide patterns that point to severe ozone depletion. If such an event happened in our time, the effects would unfold in stages. First, the upper atmosphere would be hit with a flood of gamma radiation, shattering molecules and producing nitrogen oxides. These compounds would rapidly eat away at the ozone layer, reducing it by as much as 50% or more. Within days, ultraviolet radiation from the sun, normally filtered by ozone, would begin striking the surface at dangerous levels. Crops would wither, plankton at the base of ocean food chains would die en masse, and unprotected skin could burn in minutes. That would only be the start. In the months following, the altered atmosphere could cause cooling similar to a nuclear winter. Less sunlight would reach the ground due to chemical haze, disrupting photosynthesis and plunging temperatures worldwide. This sudden climate shift, combined with UV radiation, would stress ecosystems to the breaking point. Even if humans survived the initial burst and radiation, the collapse of food chains could lead to famine on a scale never seen before in history. Meanwhile, cosmic rays from the burst would continue to pour in, penetrating deep into the atmosphere and even reaching the surface. These high-energy particles would subtly increase radiation levels, damaging DNA in living organisms and raising cancer rates for decades. Infrastructure like power grids and satellites could also be affected not by the gamma rays themselves, which are absorbed high in the atmosphere, but by the secondary particle showers and electromagnetic disturbances they trigger. What's sobering is how little warning we'd have. Long-duration GRBs, caused by collapsing massive stars, might give us clues if we're watching a known progenitor star closely. But most of the time, the final collapse happens without much external sign. Short-duration bursts produced by neutron-star collisions give us even less. Even with gravitational wave detectors, we'd likely have only seconds to minutes of warning before the radiation arrived. From a cosmic safety perspective, our position in the Milky Way isn't the worst, but it's far from perfect. The galaxy is a sprawling disk of hundreds of billions of stars, with spiral arms where new stars are constantly forming. These active star-forming regions are where the most massive, short-lived stars emerge, the exact type of stars that can become long-duration GRB engines. Fortunately, our solar system currently sits in a relatively quiet patch between the Perseus and Sagittarius arms, a sort of galactic suburb with fewer high-energy hazards. However, our position is not fixed. As the Sun orbits the galactic center over the course of 230 million years, it sweeps through different neighborhoods, some bustling with intense starbirth, others calm and dim. Every few tens of millions of years, we pass closer to denser clusters of massive stars, which increases the statistical likelihood of being within the danger zone for a GRB. On geological timescales, these periodic close encounters could line up with mass extinction patterns in Earth's fossil record. To better understand and map these risks, astronomers are using the European Space Agency's Gaia mission, which is charting the positions, distances, and motions of over 1 billion stars. This unprecedented 3D map of the Milky Way allows researchers to identify where massive stars are located, how they're moving, and, crucially, how their rotational axes are oriented. In theory, this could allow us to create a hazard map of the galaxy, showing where potential GRB progenitors are and whether their death beams could ever point our way. But there's a complication. Not all gamma-ray bursts are tightly focused, while many have extremely narrow jets, meaning you'd need to be exactly in the beam's path to feel the full force. Some show signs of wider or even layered jet structures. In these cases, even if Earth is slightly off-axis, we could still get a damaging dose of radiation. The relationship between beam width, energy, and impact radius is still an active area of study, and every new burst detected helps refine our models. Interestingly, gamma-ray bursts aren't evenly distributed across all galaxies. They occur more often in smaller metal-poor galaxies. Metal-poor here doesn't mean a lack of gold or silver, but a scarcity of heavy elements like iron, carbon, and oxygen. These elements, forged in earlier generations of stars, influence how a star evolves. In low metallicity environments, massive stars lose less mass over their lifetimes, allowing them to maintain the extreme rotation speeds necessary to form the narrow, powerful jets that define a GRB. The Milky Way is relatively metal-rich compared to many galaxies where GRBs are most common. That's good news. It means our overall GRB rate is probably lower, but it's not zero. Pockets of low metallicity still exist within our galaxy, especially in outer regions and in certain star-forming clusters. These are the cosmic hot zones astronomers keep a close watch on. To detect bursts, NASA and other space agencies maintain a global early warning system called the Gamma Ray Coordinate Network, GCN. This network links satellites like SWIFT, Fermi, and Integral with ground-based observatories. When a burst is detected, its location is transmitted to astronomers around the world within seconds. For distant GRBS, which is almost all of them, this system is mainly for research, but if one were detected in our own galaxy, the alert would also serve as a warning. Unfortunately, that warning wouldn't help much in terms of protection. Gamma rays travel at the speed of light, so by the time we see a burst, the radiation has already arrived. The only real utility in detection would be for post-event analysis, understanding what just happened and how to respond to the fallout. And what would that fallout look like for us? The first priority would be survival of critical food sources. With UV radiation levels spiking due to ozone depletion, traditional agriculture could collapse. Emergency strategies might involve moving food production indoors, using greenhouses with UV-blocking materials, or accelerating the development of genetically engineered crops resistant to radiation. Seed vaults, like the Svalbard Global Seed Vault in Norway, would become lifelines for restarting agriculture once conditions stabilized. Ecologically, marine plankton, the foundation of ocean food chains, would be devastated by UV penetration. This could ripple upward, collapsing fisheries and depriving billions of people of their primary protein source. On land, increased cancer rates in humans and animals would strain medical systems already under the pressure of famine and economic breakdown. In terms of infrastructure, satellites could be temporarily disabled or damaged by the burst's secondary effects, cutting off global communications and navigation. Power grids might be affected if cosmic ray showers in